All right, hello everybody. Today we're going to be looking at section 10-2, which is lines tangent to a circle. The first thing we'll need to know is what does that mean, right? We just came from trigonometry where we learned sine, cosine, and tangent. This is a different way to think about tangent. This isn't really related to trigonometry except for in a very broad way when you get very high in mathematics. What we want to talk about as being tangent is if we have a line that touches a circle in exactly one spot, we say that that line is tangent to the circle. So our definition of tangent means touching one time. So tangent, a line that intersects a circle at exactly one point. And those tangent lines give us a few different ways to think about circles. We can draw some more lines into a diagram with tangent lines, and we can measure certain areas. So the first thing we can talk about is the tangent and perpendicular theorem, which tells us if we have a tangent and it is tangent to the circle, in this case, at this point. Tangent at this point means point P is where that line touches the circle. Then we can say for certain that PC, that tangent point to the center, and AB are perpendicular. There's a right angle there. Always good to find right angles because then we can find right triangles. So we say if capital B, is tangent to circle C, remember that means the circle with its center at point C, at P, then we know AB is perpendicular to CP, and that's going to allow us to find those right angles and right triangles. The final theorem that we have for today is the two tangent theorem. So here you can see from point A, there are two tangent lines. If we went from A to B and kept going, that line would go away from the circle and be a tangent line. Same thing if we went from A to C and kept going, that line would go away from the circle. So it's a tangent line. So we have two tangents hitting the circle from the same exterior common endpoint. We see that they are perpendicular to the radius from the center to point B and the center to point C because of the tangent and perpendicular theorem. But what we can also say is that in this case, AB will be congruent to AC. That's our two tangent theorem. So we can write, if we have two tangents to the circle from a common endpoint, we'll give them some names. If AB and AC are tangent to a circle, and have a common endpoint, like where they both end at A, and have a common endpoint, then AB is congruent to AC, and that can help us to find some more information as well. So coming down here, we're going to explore why our tangents are perpendicular to a circle like this. Rinaldo says that parallel lines intersect a circle at opposite ends of the same diameter. If a line is tangent to a circle, then the radius of the circle is perpendicular to the line at the point of tangency. Does this fact support Rinaldo's conjecture and explain? Well, let's see. If this line is tangent to the circle at this radius, I can then extend radius XR to become a diameter, right? That radius just needs to be doubled, and now it's a diameter. And if I draw the line which is tangent to this point in the circle, it's going to make a right angle with this diameter. So let me draw that. Let's see. Sometimes this can be a little tricky to draw. All right, there we go. So now we know that this point is at a right angle with that diameter because we know that the point of tangency is always going to create perpendicular lines. So now I can say, well, look, this line up at the top and this line down at the bottom, they're both perpendicular to the same line. We had that as a theorem a long time ago. If two lines are perpendicular to the same line, they must be parallel to each other. Let's write that. You can say yes. Two lines that are both parallel to the same line. Two lines that are both parallel to the same line. Oops, are both perpendicular to the same line, sorry. Are both perpendicular to the same line. Will be parallel to each other. Will be parallel, got our parallel symbol, to each other. So yeah, those tangents can be shown if they're on both sides of a circle to be parallel lines. What's another way we can use tangents? We can use tangents a lot to create right triangles. So this question says, is KJ tangent to circle P at J? So this line looks like it hits the circle at J, but we don't necessarily know. Maybe it goes really close to the circle but outside of it. Or maybe it goes inside the circle a little bit and intersects the circle twice. How would we know if KJ was tangent to the circle? Well, we know because of the tangent and perpendicular theorem that if KJ was tangent to the circle, then KJ and JP would have to be perpendicular to each other. There would have to be a right angle here. So if we can find a right angle, if we can prove that there is a right angle here, then we will be proving that KJ is a tangent line to the circle. How do we prove whether there's a right angle in a triangle? We use the converse of the Pythagorean theorem, where we test to see if a squared plus b squared equals c squared. So let's do that. We'll have our a squared, 9 squared, plus our b squared, 6 squared. Does it equal c, which is 10 squared, right? 10 being our 4 plus 6. So we take 81 plus 36 equals 100. 81 plus 36 is 117. That doesn't equal 100. So that is not a right angle. If it was, the Pythagorean theorem would work. So you can say, no, it's not, not a right angle. And since it's not a right angle, that means that KJ, of course, is not a tangent line. Keeping on, got another idea. In this case, they tell us that ST is tangent to circle R. So ST here and SR have to be at a right angle to one another because they're tangent. We want to find the radius of circle R. Looks like I've got a right triangle here. My unknowns are these two radius pieces. But since I have a right triangle, I can use the Pythagorean theorem to find the way they relate to one another and find my answer that way. So let's do that. I've got my small side, x squared, plus my other small side, 24 squared, equals my long side, RT, that's x plus 18 squared. Keep in mind when you're doing these problems, remember that the right angle is on sort of the outer edge of the circle. People often want to say this is a right angle and use ST as the hypotenuse, but it's not. S is the right angle and RT is the hypotenuse. So now we solve, right? So we've got x squared plus 24 squared is 576. X plus 18 squared, that's the same thing as doing x plus 18 times x plus 18, or foiling or multiplying with the distributive property. That's going to give us x squared plus 36x plus 18 squared, which is 324. So now we've got some quadratics to work with, but you'll notice that there's an x squared on both sides. So those just cancel out. And we are ending up with 576 equals 36x plus 324. Then we will keep solving, subtract 324 from both sides. And we get 252 equals 36x, divide by 36, and we end up with 7 equals x. Check the problem. They asked what is the radius of circle R. Since the radius is x, then the radius is 7, and 7 is our answer there. All right, here's another way we can use it. If LK is tangent to circle N at L, like it is here, what is KN? We're looking for this piece, which is the hypotenuse. So same idea here. We're going to be using the Pythagorean theorem. The only thing that's different with the right triangle we have right here is that we don't have a label for LN. But notice that LN is the radius of the circle. So is this piece from N to the edge that's labeled with a 9. Since all the radii of a circle are the same length, I can call LN 9 units long. That is the same amount because it's a radius. Then I need to think about the fact that Kn is shown as two pieces. It's an x minus 1 and a 9. If I combine together x minus 1 plus 9 to combine my like terms, I get x plus 8. So I can call my entire segment Kn x plus 8. So let's go ahead and use the Pythagorean theorem. We'll take our two short sides. We've got x plus 5 squared plus 9 squared equals our long side, which we just said was x plus 8 squared. Once again, I'm going to FOIL, or use the distributive property, because x plus 5 squared is like x plus 5 times x plus 5. So that's x squared plus 10x plus 25 plus 9 squared, which is 81, equals, and then the other side, x plus 8 squared, when we distribute, is x squared plus 16x plus 64. Once again, both of your equations have an x squared on one side, so we can cancel it out and combine our like terms. We've got 10x plus 106 equals 16x plus 64. Then we can go through and subtract. Oops. And then subtract 64. And so if 42 equals 6x, we divide both sides by 6, and we get x equals 7. X won't always equal 7. It just happens to in these couple of examples here. So then we say, all right, if x equals 7, we are being asked what is Kn. Kn was represented by the equation, or the expression, x plus 8. So 7 plus 8 tells us Kn is 15 units. All right, here's a way that we can use the two tangent theorem. Here in this circle, we have two tangent lines coming from the same endpoint z. So using the two tangent theorem, we can apply this information. It says if tx equals 12 and tz equals 20, what are xz and yz? All right, so we're looking for the third side of this triangle. And we can do that by using the Pythagorean theorem to find the other short leg here. So we can say 12 squared plus x squared equals 20 squared. And when you solve the Pythagorean theorem there, you learn that x equals 16. So zx is 16. They also asked us, what is xy? We can say, oh, well, because of the two tangent theorem, zx and yz will be the same quantity. So yz will also be 16. So both of them are 16, and that is your solution. Number 4, find measures involving tangent lines, another expression or application of the two tangent theorem. Here we're looking for the perimeter of A, B, C, D. And if you'll notice, it looks a little bit complicated at first. But if I look at each of the points that I have in this quadrilateral, I'm noticing that I have two tangent lines to the same, or from the same endpoint. So this two tangent theorem says that if A to the tangent point is 7 units, then A to the other tangent point is also 7 units. If B to the tangent point is 2 units, then the other tangent of B is 2 units. Same thing with the other tangent of C being 3 units, and the other tangent of D being 6 units. Then we can add everything together. We're asked for the perimeter of ABCD. So when we add all of those numbers together, we should get 36 as the perimeter of ABCD. So it makes it very simple there. One more example. I really like this example a lot. It uses real-world data and real-world ideas. And it is a way that these tangent lines are really used. This is something that people would do exactly this math to find out the answer. So a satellite requires a line of sight for communication. Between the ground stations furthest from the satellite, what is the amount of time needed for a signal to go from one station up to the satellite and down to the other station? So they're asking the amount of time we need. We want to know how long it takes to send a signal from this side to this side of the Earth through that satellite. The first thing I'm going to do, and this is something we're going to do a lot in this chapter, is we're going to find some convenient places to draw in the radius. They told us that the radius was 6,371 kilometers. That's good, but we can probably make it a more convenient measurement by drawing that same radius from the center to the ground station. So that's 6,371. And we'll do the same thing from the center to the other ground station. We can also draw another convenient radius from the center to the line where our satellite is above the Earth, and that is another 6,371 kilometers. Since we're being asked how long it takes the signal to go from the ground station to the satellite, we need to know the distance from the ground station to the satellite. Since the satellite requires a line of sight, the furthest away spot on the Earth it could be is the tangent point. Because after that, this satellite signal is going to be going away from Earth. So it goes towards Earth all the way as far as it can, and then it goes away from Earth, meaning this line is tangent to the circle, and there will be a right angle between the line and the radius of the Earth. That gives us a right triangle where we can then use the Pythagorean theorem to find the length of the missing side. First, we should find the length of the hypotenuse because it gives us the radius of the Earth and the distance of the satellite above the Earth. So that's going to be 35,786 plus 6,371. That gives us a hypotenuse of 42,157. So that's our long side of our triangle. So let's use the Pythagorean theorem. We've got the radius of the circle, 6,371 squared, plus the other short side, right? Here's one short side, here's the other short leg, that's x squared, equals the hypotenuse, distance from the center of the Earth to the satellite, 42,157 squared. So 6,371 squared. You can do all this math. This is just regular numbers math. Once you solve the formula, once you solve the Pythagorean theorem there, you find that x is equal to 41,672.8 kilometers. So then you say, well, what does that represent? That represents the distance between the ground station and the satellite, this distance right here. But we don't want the distance, we want the time it takes, okay? So we want to say, if I am taking 41,672 kilometers, I'm gonna double that first because I need to send my signal up to the satellite and back down to the ground station. So I'm gonna take 41,672.8 times 2 to give me 83,345.6. That's my entire trip. That's the whole distance that the signal has to go. To figure out how long it will take, right, speed equals distance divided by time, and so time equals distance divided by speed. Sorry. So we can take our speed of our distance equals 83,345.6 kilometers. Divide that by our speed of radio waves, which is 300,000 kilometers per second. And we end up with 0.278 seconds. I can't spell seconds. 0.278 seconds. And that is how long it takes for the satellite signal to go from a ground station to the satellite and back to the other ground station. All right, so go ahead and work on your problems associated with this section. Make sure if you've got any questions to ask them to me the next time you see me. All right, have a wonderful day. I will talk to you later. Bye.